All right, so the lecture before this, we ended up manipulating Pervnert to write it in terms of mass and, molar mass, okay? So what we're going to do for today is we're going to manipulate Pervnert again, but we're going to do it in terms of density. So again, we've got PV equals nRT. This is on your equation sheet. And then also on your equation sheet is that moles equals, it's the same as mass over molar mass. So you can take and plug this in right here. So this is PV equals mass over molar mass RT. So let's talk about what density is. What do you remember density is? Density is mass over volume. So look, I have both of those terms right here. I have mass and I have volume. So I'm going to get mass over volume together. So I'm going to put molar mass over here, multiply both sides by molar mass. We're just doing some algebraic manipulations. Okay? And then divide by V, okay? So that gets rid of my V. Oopsies, sorry. Okay, and then, right, this is density right here. So this guy, this whole term right here is density. So I'm going to divide both sides by RT so I can get density by itself, RT. Okay, so this is density equals molar mass, pressure, gas law constant, T. Okay, so this is the equation for the ideal gas law in terms of density. Now this can also be rearranged to solve for molar mass, let's say. So that means I'd put the RT back over here if I wanted it to be molar mass. Well, actually, I'm going to do this first. Oops. Okay, so this is one way. Now, if I rearrange this, I'll put the RT, so it'd be DRT, and then I divide both sides by P, and that's molar mass. So this is just a different rearrangement. So there's like a mnemonic device. Meow, the cat kicks dirt over its pee. I have no idea who made that up, but that's a way that kids memorize it this way, because again, it's not on your equation sheet, but you should be able to figure it out algebraically. So we will use this concept to figure out density of gases. So we're going to find the density of carbon tetrachloride vapor. Remember, vapor means gas, and I give you a pressure and I give you a temperature. So 714 torr, 125 Celsius. So I'll write that up here, 714 torr, 125 Celsius. Okay, and we want density. Well, right, PV equals nRT. All right, I'm going to always do it this way because I don't expect that you will, memorize everything. So I'm going to just keep doing the conversions. Replace your moles with mass over molar mass. Okay, and then let's rearrange to get density. So molar mass comes up here. Yes. Okay, divide by V, divide by V. Whoopsies. I need to make my eraser a little bit smaller. Okay. Now this right here is density. This is density. So divide both sides by RT. And we get molar mass times pressure divided by gas law constant times T. So we're just going to plug in. So what's the molar mass? Well, they said it was carbon tetrachloride. So CCl4. What's that guy's molar mass? I don't know, 35. 153.81. Is that right? Grams per mole. There's the molar mass. That's what this is. Pressure is 714 torr. R is the gas law constant. Now I'm going to use the 62.36 because that's the one that has torr in it. And T is temperature in Kelvin. So 125 plus 273 is 398 Kelvin. And then let's look at how units cancel. So look, moles cancel, Kelvin cancel, torr cancel, and you're left with grams divided by liters. That is a unit for density. Grams divided by liters. So this times this, and then hit divide 62.36, and then hit divide again 398, and you will get the substance's density. And so you should get 4.43 grams per liter. Now notice the units for density of gases uses the bigger unit, right? So like before this chapter, when we talked about density, we would talk about it like in terms of grams per milliliter or grams per centimeter cubed. Oh boy. So grams per milliliter, grams per centimeter cubed. These volume units tend to be smaller. This is a bigger volume unit, which should make sense for gases, right? Because gases take up a lot of space. So that's why you'll see it written as a bigger volume unit. Okay. So next, I give you a gas and I tell you its density, and now I want its molar mass, and I give you a temperature and a pressure. So, 2.50 grams per liter, negative 10 degrees Celsius. Let's see, 800 torr. I'm just writing it so I don't forget it. 800 torr. Oops. All right, so we're given density, so we have to use, so PV equals nRT. All right, I'm going to replace the N with mass over molar mass, because that's what moles is. Okay, I want to know molar mass in this problem, meaning I'm going to isolate molar mass. That's this guy. So molar mass PV equals nRT, right? So divide both sides by PV. And now you got to be careful. So this right here, mass over volume, is density. So really what it is molar mass equals density RT over P. Meow dirt over P. Okay. So again, I rewrote this mass over volume as density. So at this point, it's just plug and chug now. So what was the density? 2.50 grams per liter. What is the R constant? Let's see, we're going to use that 62.36 because my pressure is in torr. So liter torr over mole Kelvin. And then my temperature is negative 10, so that's 263 Kelvin. Divided by pressure, which is 800 torr. So let's look at how the units cancel out. So look at torr cancels, Kelvin cancels, liter cancel, and you're left with grams over moles. That is the unit for molar mass. So multiply all three of these numbers out and then divide by 800 and you will get the answer. So let's look back what that is. 51.3 grams per mole. That is the molar mass of the gas. All right. So we talked about gases, and we always kind of assume, and incorrectly so, that gases have low density, right? They all float, like, right? You always think of like helium or oxygen or all the gases in our atmospheres float, and it's true. A lot of them are very, very low density, but there are some ones that have high density, meaning they sink in air. So I'll show you this video of a low density gas that you're very familiar with.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and my voice gets really low, although somehow I'm still funny. It's scientific!
All right, so as you can see, that sulfur hexafluoride gas is super dense. Now, it is so dense that it will sink in air, okay, because it's more dense than air, and it is so dense that it can actually hold up aluminum foil. So check this out. They take this aquarium, this empty aquarium, and they fill it with sulfur hexafluoride and cover it, okay, so it just traps all the sulfur hexafluoride, and they take it off and they put this aluminum foil boat, okay, on top of it. So you can kind of check this out, how dense sulfur hexafluoride is. And it's so air dissipates, or air diffuses out. Okay. So again, that's a sample of a gas that has high density, not as common as what we're used to with. Okay. All right. So on to the next topic of stoichiometry with gases. So just like we can do stoichiometry in a chemical reaction, we can do it with gases. And the reason we can do that is because we have multiple ways now to get to moles. So right in the beginning, whenever you first learned stoichiometry, it was grams to moles. Okay. That was before you even came to me. And then last chapter, we learned that molarity times volume could get you moles. So we did stoichiometry with solutions, because remember, molarity and volume tend to be for solutions. Well, now this chapter, we have an equation that also can get us to moles, okay? So this is going to be a new way to do stoichiometry. So once you're in moles, everything else is the same. So again, remember, this is called the ideal gas law, meaning you can only plug information about gases in here. It's called the ideal gas law for that reason, right? So we're going to make ammonia, we're going to make ammonium sulfate by reacting ammonia and sulfuric acid. And they ask you what volume of ammonia gas, and they give you a temperature and a pressure, will be needed to produce a certain mass of ammonium sulfate. So here's the answer, so we're going to write this out. So ammonia and sulfuric acid react to make ammonium sulfate. Let's see, I need 2 of these guys. That gives me 6 hydrogens plus 2 more is 8, and then that's 8. Sweet, and everything else is good. Okay, so again, let's look at the problem. I give you a pressure and a temperature, which is not enough to use Pervner yet, but we do have grams of ammonium sulfate, so we can turn grams of ammonium sulfate into moles of ammonium sulfate, right? So 5 times 10 to the third. 5 times 10 to the third is the same as 5,000. Okay, so 5.00 times 10 to the third grams of ammonium sulfate. That's how much they want to produce. So we can turn grams into moles. I'll have to look up ammonium sulfate's molar mass. 132.14 grams per 1 mole. And then now that we're at moles, I want to know about ammonia, right? So I will jump. I will do mole ratios for every 1 mole of ammonium sulfate that reacts. 2 moles of ammonia are required for the reaction. Okay, and now I will have moles of ammonia. Well, if I now have moles, which is N, and I have T, and I have P, I can rearrange Pervner, right? I have P, I have V, I have I have P, I have moles, I have R because it's constant, and I have T. I can rearrange and solve for V. So all we needed to do was just this first step of stoichiometry to get moles of the gas, and now we're just going to plug into Pervner. So let's find out what this moles is. Remember, do not round till the very end. You don't want to be rounding your numbers. If you write it down rounded, that's fine, but keep the whole number in your calculator. So this is like 75.677 something moles. Okay, so write PV equals nRT, and they want volume, so V equals nRT over P. So let's plug in. So my moles, 75.677 something moles. Okay, the R constant. I think the pressure was in atmospheres, right? So we're going to use the R that goes with atmospheres. Oops. That's the 0.08. 0.08206 liter atmosphere over mole Kelvin. And then the temperature, I already forgot that also, was 78 Celsius, so we can't use 78, we have to use 351. And then divide by pressure, which was 1.66 atmospheres. So the units, moles cancel, Kelvin cancel, atmospheres cancels, and you're left with liters, which is a unit for volume. So if you go back with 3 sig figs as your final answer, it's 1310, which is a huge number, but you've got to think about this. You're trying to make 5,000 grams of ammonium sulfate, so that is a pretty big amount, so it would make sense that you would probably need a lot of gas to make 5,000 grams of ammonium sulfate from ammonia. Again, it's, the first part was stoichiometry that we learned, or that you guys learned last year, okay? This part is old stuff right here. The new part is actually just using it to plug into here. Okay? So, let's try another one. Octane reacting with air at 0 degrees Celsius, so 101.3 kilopascals. What volume of CO2 will be produced? Okay, so let's write out the reaction first. So C8H18 reacting with air means plus O2. This should look like a combustion reaction to you. So CO2 plus H2O. So look at, we need 8 carbons. Okay. 18, so 9 times 2 is 18. Ugh, yucky. 8 times 2 is 16 plus 9 is 25. So the way we tend to do this is write this as a fraction, right? So 25 over 2, right? Because 25 halves times 2, right here, is 25. All right, sorry about that. So 25 halves times 2 is 25, right? But we can't leave this as a fraction, so we multiply everything by 2, because that will give us a 2 here. Hold on once. All right, so this is a 2 here, and then 25 over 2 times 2 is 25. So this is gone. What's 8 times 2? 16. What's 9 times 2? 18. Okay, so that's our balanced combustion reaction. So let's go back to the problem. We're burning 57 grams of octane. So if you know grams of octane, you can turn it into moles. And then if you know moles of octane, you can do mole to mole ratios to get carbon dioxide. So let's do that. So 57 grams of octane, C8H18. I guess I'm going to have to Google its molar mass. .23 grams for every 1 mole of octane. And then for every 2 moles of octane, there are 16 moles, and you can write this as 8 over 1 if you want, it doesn't matter, 16 moles of carbon dioxide. All right, so now we have moles of carbon dioxide. So 57, 4.23 is 399 moles, 3.99 something moles of CO2. Well, if you know moles of CO2 now, you can plug into Perfner to solve for, what are we trying to find? Volume? We're trying to find volume. So PV equals nRT. So V equals nRT over P. So what's my moles? My moles are 3.99 moles. What's my R? That one was kilopascals, and the one that goes with kilopascals is 8.314 liter kilopascal over mole Kelvin. And the T is temperature in Kelvin. I think it was 0 Celsius, so that's 273 Kelvin. And then the pressure was 101.3 kilopascals. Okay, so moles cancel, kilopascals cancel, Kelvin cancel, and we're left with liters. All right, so you plug it all in, and you get, let's see what the answer is, 89 liters. Okay, 89 liters, 2 sig figs, because this is 2 sig figs right here. Okay, now, if you didn't notice, which it's not it's easy to miss. There is something special happening in this chemical reaction, and that special thing that's happening is that we are at STP. This is standard temperature, and this is standard pressure. So if you don't remember, 1 atmosphere is the same as 760 torr, or millimeters of mercury, right? Is equal to 101.3 kilopascals. Okay, these are all the same. These are standard pressures. And then 0 Celsius or 273 Kelvin is standard temperature. So something special in the gases chapter about STP is that 1 mole of any gas occupies 22.4 liters of space. And I showed you how they got this number by rearranging Pervner with these conditions in there. So what you can actually do is, if you do recognize this in the problem, you can actually do something a little bit different. Now, it would start off the same. So grams to moles, moles of octane to moles of carbon dioxide. Now, here is what's cool is if you are at STP, you can take this and go straight to liters. And the reason you can, so, oops, I don't want that to be red. 1 mole of any gas at STP occupies 22.4 liters of space. So then look, you're left with liters, right? Grams, cancel, mole, liters. And this is just an alternate way to do this problem if you recognize that you're at STP. Now, you can only do this if you're at STP. Any other conditions, you would have to plug into Pervner. So now, if you don't recognize you're at STP, Pervner will still be good. You can still use Pervner, but if you do, you can do this step. Again, if you don't remember or recognize it, Pervner will still work and get you the right answer, but this is a possibility of a different way to do it, or a different approach to get the final answer. Okay. Again, you can only do that if you're at STP. All right, so let's do another one. We have methane burning in air, or oxygen, I should say, and we have 8.025 grams of methane react at a certain temperature and pressure, and I want to know what volume of O2 reacts. Okay, so again, obviously, I'm giving you methane, I'm asking about oxygen. This is going to be stoichiometry. All right, so let's write out the reaction. Methane and oxygen making carbon dioxide and water. Looks like I need a 2 here and a 2 here, and that's it. Okay, so how many grams? It was 8.025 grams of methane. Okay, turn grams into moles. Okay, and they want to know about oxygen, right? So now we're going to do mole ratios. For every 1 mole of methane reacting, right, there's a 1 here, there's 2 moles of oxygen reacting. So now that gives me moles of oxygen. Now I cannot go straight to volume. I can't do that 1 mole is 22.4 liters because this is not STP. So I'm going to have to use Pervner now to get volume. Now I have pressure and I have temperature, so I'll just rearrange. Remember, Pervner, I've done this a couple times now, so I'm not going to do it again. V is nRT over P. So let's see, what do we get? 8.025. I think this is going to be 1, right? 1 mole. This is like exactly 1.00 moles. The R will do the 62.36. Okay, over mole Kelvin. That's the R that goes with torr. The temperature was 25 Celsius, which is 298 Kelvin. All divided by the pressure, which was 800 torr. So let's look. Moles. Oops. Moles, cancel, Kelvin, cancel, torr, cancel. You're left with liters. So if we look back and you calculate all of that out, you get 23.3 liters of O2. Okay, and then it asks you what volume of carbon dioxide and water are produced. So we'll talk about water last, but let's do carbon dioxide. Well, you have 2 options. The first option for this is you would start off exactly the same. So moles of, grams of methane to moles of methane. 1 mole of methane, and now instead of oxygen, Instead of oxygen, we're going to, what, carbon dioxide? And it's a 1-to-1 ratio. So now we have half of a mole. So here's the thing. If you have half of a mole, okay, the only thing changing in this equation is the moles. The R constant is the same. This is still at the same temperature and still the same pressure. Let's see. This is 0.5. So you'll notice if the moles are changing by half, the volume is going to change by half because nothing else was different. So what you can actually do, so this is 0.5 moles. Okay. So when you calculate it out, you'll notice that you'll get half of what you got for oxygen. 11.7 is half of what you got for oxygen. Technically, you can do what are known as volume ratios, where you treat them like mole ratios as long as the conditions aren't changing, meaning once you know one of the substance's volumes, you can use, sorry, I keep switching the wrong one. You can use that substance's volume to find the other one. So like we said, what was it, 22.3 or 23.3? Okay. So, again, you can plug the moles in. There's no wrong way to do this. That's fine. Or you could have said, okay, well, let me see. Where am I going to erase this? You could have said, okay, well, I actually know I just solved for oxygen. So it's 23.3 liters of oxygen. And then you can treat these moles like volume ratios. For every 2 liters of oxygen that react, 1 liter of carbon dioxide is produced. So you'd call them like liter ratios instead of mole ratios. And again, you can do this because this and this and this all stayed the same. The only thing changing was moles. And then again, you would just get 23.3 divided by 2 is 11.7. So that is an alternate way to do this, is this volume ratio, is once you find the volume of one substance, you can use ratios to find the other one instead of plugging back into Pervner. Now, Pervner isn't wrong. It'll still get you an answer, but this is kind of like a shortcut way if you can remember it. Okay, and then water is a little bit funky, so I'm going to do this. Notice that I put water as milliliters, and the reason it's in milliliters is because in general, a water in a chemical reaction is a liquid, and so we usually talk about liquids fairly often in terms of milliliters. So what I'm going to do here is I'm going to start it off the same. I'm going to say, okay, my grams of methane to moles of methane, and then I'm going to do moles of methane to moles of water. So 1 mole of methane that reacts, 2 moles of water are produced. And then instead of plugging into Pervner, because water is a liquid, right? Pervner is for gases, and we're going to assume under room conditions that this is going to be a liquid. 1 mole of water is 18.02 grams, and then the density of water is 1 gram for 1 milliliter. So I use the density of water to turn its mass into volume of milliliters. Again, you're not going to plug it into Pervner because it's a liquid. It's not a gas. Remember, this is the ideal gas law. It's not the ideal liquid law. It's not the ideal solid law. It's for gases only. So I just turn my moles into grams and my grams into milliliters with density and molar mass. Okay. So that's how that. So right, 8 divided by 16 is a half, times 2 is 1. 1 times 18 is 18. And then times 1 is 1, or 18 still. I didn't change the number. So that's how you get the milliliters. Okay, so that was those answers. All right, potassium chlorate is heated. Now, we've done this reaction in here before. 5 times 10 to the second. I'm going to try to write these numbers down so I don't forget them. 5 times 10 to the second. Oh, already forgot them. Milliliters and 1.108 atmospheres and 39 degrees Celsius. Okay. And then we're taking potassium chlorate, that's KClO3, and we're heating it. Remember, heating can often be represented by a triangle over the reaction arrow. KCl plus O2. So this is 2, 2, 3. Okay, and then, so let's see how this problem. This problem is different than the other stoichiometry ones we've been doing in the sense that all of the data I gave you this time was for the gas. So all the other times I gave you masses first, and then we turned gram into moles, did mole to mole ratios, and plugged into pervnert. We're going to do the opposite this time. I give you volume of the gas, I give you pressure and temperature. I have enough information to find moles of the oxygen gas, so I'm going to plug into pervnert first this time instead of last because I have enough information to do that. So I have, right, so PV equals nRT. So I have P, I have V, you always have R, and you have T, so rearrange. PV over RT is moles. So what was the pressure? Well, it's 1.108 atmospheres. What was the volume? Now, careful, this number was in milliliters, okay? And you can only plug liters into the pervnert equation. So this 5 times 10 to the 2 is 500. So in liters, that's 0.5. You can only plug liters into pervnert, okay? And then the R is 0.08206 liters times atmosphere over mole times Kelvin. And then temperature is 39 Celsius, so 39 plus 273 is 312 Kelvin. So atmospheres cancel, liters cancel, Kelvin cancel, and we're left with moles, which is what N is, right? So let's take a second. I'm going to calculate this out. Okay, so this is the amount of moles of O2. Now they asked, so that's this guy. Well, they asked, though, about potassium chlorate, the mass. So now that I'm at moles, I used pervnert as my tool to get me moles because all this information was about a gas. I can just do my normal stoichiometry, do mole to mole ratios, and then turn moles into grams because they did specifically ask for grams. So 0.0216 something, something, something. I left the whole number in my calculator, moles of O2. For every 3 moles of O2 that react, 2 moles of potassium chlorate, for every 3 moles of O2 that are produced, 2 moles of potassium chlorate are required, and then 1 mole of potassium chlorate, I have no idea what this guy's molar mass is. Let's Google it. It is 122.55 grams. So you take that, divide by 3 times 2 times 122.55, and we get 1.77 grams of potassium chlorate. So if this is how much oxygen you produce, that's how much potassium chlorate would have been required. Okay? All right, so that's it for stoichiometry. So I'm going to introduce you to this first concept of collecting gas over water. For some reason, this can be confusing to kids, so I'm going to do my best to explain it before we end. So here's the thing. If you look in your book or on a chart, okay, you'll see, let's see. No, it's not going to let me switch back and forth. Okay, so collecting gas over water can sometimes be a confusing concept for students. So the whole point of this is at the surface of any liquid, no matter what temperature the liquid is, there are always some small amount or big amount, depending on the temperature of the liquid, of gas vapor. So like you have a bunch of liquid water right here, but sitting on the surface of the water are some water vapor molecules. And water vapor molecules exert pressure, a partial pressure. We call it the vapor pressure of water. So like in a room, if you have a total pressure, that's going to be the pressure of everything in the room, plus the tiny bit of, like, let's say we're collecting it over water, of the pressure that comes from the fact that there are water vapor molecules sitting on the surface of the water. And so it contributes to the total pressure of the room. So when you collect a gas from like an experiment over water, the total pressure of the room, this is like the barometric pressure, the total pressure, is the pressure of the gas that you're collecting whatever gas it is, plus the tiny bit that may come from the fact that water, if you're collecting it over water, water exerts some pressure. So if you were to look in your book, you'll see like a bunch of different temperatures of water, because temperature is going to affect vapor pressure and different vapor pressures. Now you should notice something about this. So look at, so like room temperature is about 25 Celsius. So if you collect a gas over water, there's liquid water in a container, there's a tiny bit of pressure that the water exerts. And again, that happens because there's little vapor water molecules sitting on the surface of the water. It's not a lot, this is not a ton of pressure, but it is some pressure, so we have to account for it, okay? Now you should notice something. We discussed the whole idea that vapor pressure, boiling point is when vapor pressure equals atmospheric pressure. Boiling point can be facilitated by boiling. Can be help facilitate by. I'm misspeaking. You can help facilitate something to boil by heating it up. That's one way to do it. But by definition, boiling has nothing to do with heat. You just have to get the pressure of the vapor pressure of the whatever liquid you're trying to boil, and get it to turn into meet atmospheric pressure so it can escape into the gas phase. Meaning you can take water and remove pressure from it, like put it in a vacuum, and it will boil. It's not hot, but it's boiling because it's able to escape in the gas phase because it has less stuff pushing it down and keeping it in as a liquid. So you'll notice that the vapor pressure of water at 100, right, this is water's boiling point, is 760. Well, what is 760? 760 is atmospheric pressure. So the more you heat water up, so this is getting hotter and hotter and hotter and hotter, the more pressure it exerts, because the more you heat it up, the more it's turning into a gas, and gases exert more pressure. Again, they call these partial pressures, right, because it's only part of the pressure of the experiment when you're doing it. So if you look at this question, it says a sample of hydrogen gas is collected over water. So this is your main hint, collected over water, meaning inside the container there's water and whatever gas. So in this case, it's hydrogen gas. So the barometric pressure of the lab, this is total pressure, is 847 torr. And then I tell you, okay, well, they did this experiment at 14 degrees Celsius, and at 14 degrees Celsius, the vapor pressure of water is 12 torr. So at this temperature, this amount of water, so a little bit of water is turning into a gas, and this is how much pressure it exerts. So what is the partial pressure exerted by the dry hydrogen gas? Well, partial pressure, Dalton's law, is one pressure plus another pressure. So this is the pressure of hydrogen gas. In the total pressure of the room is the pressure of the hydrogen gas and the fact that there's water in there. This is the partial pressure of water. Now, it's not a lot, but it's enough that you have to account for it. So if the total pressure of the room is 847 torr, and I want to know how much of it's just the gas, the 12 is the water, so you subtract 12 from both sides. So, right, 847 minus 12, and that's 835. So the pressure that's coming from the hydrogen gas, it's the majority of it, 835 torr. It's the majority of the pressure. But you had to account for the tiny little bit that comes from the fact you are collecting a gas over water. Okay, so this would be, they sometimes call this the dry gas, right? We've taken the water out of the, mathematically out. So this is the pressure of the gas you collected. And again, you have to do this because water at at all these temperatures above its freezing point does exert some vapor pressure. And I know that can be confusing, but I'll try to draw again. So like you've got liquid water, and then sitting on the surface of the water are small amounts of water molecules that are in the gas phase. And so these little small amounts are what we have to account for, because anytime something is in the gas phase, it exerts at least a little bit of pressure, and it's part of the total pressure, partial pressure. So again, collecting gas over water is generally is very easy math. It's just subtraction usually, if you know total pressure and then the vapor pressure of water. Again, this number would be looked up in a chart. For you, I gave it to you right here, okay? Or you could come back here. I don't think 14 is on here, but this would be like, what's the vapor pressure of water at 22? Oh, it's 19.8. So you would subtract this number from the total pressure to get the pressure of just the dry gas. And again, the vapor pressure of water changes when temperature changes, because if you heat water up, the molecules move faster. If they move faster, they escape into the gas phase more, and so they exert more pressure the hotter that the water gets. Okay, so that is the first concept of vapor pressure and water and how to calculate it. And this is where we end it.